Have you ever really, truly stopped to wonder what the world around you is made of? I mean, your desk, that cup of coffee, the very air you're breathing. What is it, really? Well, today we're diving deep to uncover the fundamental rules of chemistry that govern, well, literally everything. And it all kicks off with a super simple question you've probably never thought to ask. So yeah, it's a huge question, right? To get our heads around it, let's start with something you see every day. We touch things, we see them, but what's going on at a level so tiny we can't possibly see it? How does it all work? Okay, think about this. It's so simple. You take a spoonful of salt, stir it into a glass of water, and poof, it's gone. But it's not really gone, is it? The water tastes salty, so it's still in there. What's the deal? This little kitchen experiment, believe it or not, holds the key to our entire story today. So if we could zoom in with some kind of super microscope, what would we see? The salt, which scientists call the solute, isn't just vanishing into thin air. Its teeny tiny particles are actually breaking apart and mingling with the water particles, the solvent, and together they form what's called a solution. But to really get how this little magic trick works, we need to meet the star of the show. All right, let's zoom in. I mean, way, way in. Past what any microscope on Earth can see, to the most basic, fundamental building block of all matter. That's it, the atom. Everything, and I mean everything, is made of atoms. You can think of them as the Lego bricks of the entire universe. It's as simple as that. But these bricks aren't just solid blocks. They have their own internal parts that decide how they connect to build everything we see and touch. So, you see, an atom isn't just one solid little ball. It's got this dense center, called the nucleus, and then it has these even tinier particles, called electrons, zipping around it in these layers or shells. And if we look even closer, inside that nucleus, we find two other kinds of particles hanging out.
And each of these little guys has its own personality, which is really just its mass and its charge. In the nucleus, we have the protons, which are positive, and the neutrons, which are, you guessed it, neutral. They make up almost all the atom's weight. Then, orbiting on the outside, you have those super light, negatively charged electrons. And these charges, the positive, the negative, and the neutral, that's the absolute key to how atoms decide to team up.
So, we've met our individual building blocks, but a single atom on its own is, well, a little lonely. How do they get together to form the incredible variety of stuff we see in our world? Now this is where it gets really cool. There are basically three ways atoms can arrange themselves. First, you've got an element. That's a substance made of only one type of atom, like pure gold or pure oxygen. Then you've got a compound, which is made of two or more different elements that are actually chemically stuck together. And finally, you have a mixture, where different things are just kind of tossed together in the same space, but with no real chemical connection. And this right here is the critical difference. In a mixture, like if you just mix some iron filings and sulfur powder, the particles are just mingled. You could literally pick them apart with tweezers or a magnet. But if you heat them up, they chemically bond and form a compound, iron sulfide. And that is a totally new substance with completely different properties. All because the atoms have truly joined forces. Right, that's the million-dollar question, isn't it? What is this chemical bond that's strong enough to hold them together? Well, it all comes down to those tiny, negatively charged electrons we saw zipping around the outside of the atom. Atoms basically form these bonds in two main ways. They can either transfer electrons from one atom to another, we call that ionic bonding, or they can share electrons between them, which is called covalent bonding. You can think of it like this. Ionic bonding is like one atom giving a gift to another, while covalent bonding is like two atoms agreeing to share a toy. Let's look at the perfect example of ionic bonding. You've got a sodium atom here, and it gives away one of its electrons to a chlorine atom. Now, because it lost a negative electron, the sodium atom has a positive charge, and the chlorine, having gained an electron, now has a negative charge. And what do opposites do? They attract. That powerful magnetic-like force is the ionic bond holding them together. And boom, just like that, you've made table salt. Okay, now for covalent bonding, the sharing model. Here we have two chlorine atoms. Each one needs one more electron to feel stable and happy. So instead of one stealing from the other, they come to a little agreement. They each put one electron into the middle and share that pair. That shared pair of electrons creates a really strong connection, a covalent bond that holds them together as a single molecule. Okay, so this is all pretty cool, but what's the point? Well, once we understand these fundamental rules, atoms, bonds, mixtures, we can actually start to use them. We can manipulate the world around us. We can pull things apart and put them back together. And you don't need a fancy lab to do it. We can prove it right in the kitchen.
Let's say you've got some rock salts, which is really just a mixture of salt and sand. How do you separate them? It's actually pretty simple. First, you grind it up to make the pieces smaller. Then, you add water. We already know the salt will dissolve, but the sand won't. It just sinks. So now you can pour the mixture through a filter to catch all the sand. Finally, you just heat the water evaporates away, and what are you left with? Pure salt crystals. See? You just used your knowledge of chemistry.
And here's another super powerful method, distillation. This trick works by separating things based on their different boiling points. Take seawater, for example. If you heat it, the pure water will boil and turn to steam long before the salt even gets warm. You can then capture that steam, cool it back down into liquid, and you're left with pure, fresh water with all the salt left behind. Pretty smart, huh? Okay, deep breath. We've covered atoms, we've covered bonds, we've covered mixtures and how to separate them. We have all the puzzle pieces on the table. So it's time to go all the way back to our original question and finally solve the mystery of the disappearing salt. And here we are, right back where we started. But now, this picture shouldn't feel like a mystery at all. Now, we know exactly what's happening at that invisible atomic level.
So here's the big reveal. Remember how salt is an ionic compound? It's made of positive sodium ions and negative chloride ions all locked together in a tight crystal structure. Well, when you drop that crystal into water, the water molecules swarm it. They use their own slight charges to literally pull the positive and negative ions apart, breaking those ionic bonds. The ions haven't vanished, they're just floating freely, completely surrounded and distributed among all the water molecules. That is what a solution is.
It might seem like a lot, I know, but getting these core ideas, atoms, bonds, compounds, and mixtures, is really the foundation for understanding how the entire world works. From the way you bake a cake to how a rocket launches into space, it's all the same set of rules. So next time you're just going about your day, take a look around. The fizz in your soda, the rust forming on a metal gate, the way soap magically cleans your hands. It's all just a story of atoms interacting, bonding, and mixing. Now that you know the language, what will you see differently?